Okay, my friends, another shocker du jour. We've been looking out into space to try to find distant objects in space. Now, this is what they're talking about. This is the Webb Space Telescope. Listen to what they have to say at the very last words. All right, it says, "It is only by the light that we can begin to understand the exotic physics that governed the galaxy near the cosmic dawn." Well, let me tell you something. They don't understand space. They don't understand what's in space. They don't understand light. They can't understand anything. And Webb telescope is a complete failure if they're trying to find things that are in a distant past, because they can't see to the distant past because of all of the fields and particles that are in their way. Light slows down. It does not say the same speed. It's extremely obvious, and it's getting to be extremely annoying that the people that should be paying attention to this refuse to engage. They won't even talk to me. And I have the evidence to prove every word I'm saying. And if you can dispute it, dispute it. Okay, originally I was going to call this nuclear electron theory, where the electrons are inside the nucleus, which they are. And this goes back to 2016. And I said everything's wrong. Light has no mass, that's wrong. Light is fixed speed, wrong. The neutrons are neutral, wrong. And then I said after that, all they have done is guesses. I'm showing you the actual particles. And then I'm going to show you how I explained all this to CERN and what they did as a response. I came up with the fact that light and dark forms of energy. Light and dark are forms of energy, both of them. Light leaves the sun as energetic particles in all kinds of different sizes, but to the tiniest size is a muon and an electron neutrino. Together they make a dirac. They call them gluons. All right, now, light pushes solar sails. It has a weight. It has a mass. It pushes things. Light has solar cells and displaces electrons, creating electricity, and they flow. When light hits solar panels, the solar cells, and they make electricity flow, they push the electrons. There's a impact. Light grows biomass, increases the weight according to the wattage. The more wattage you have on plants, the bigger they grow. Light is not seen as it transits space to Earth. Well, that's true and not true. Light blinks on and off, blip, 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 as they concuss with each other's fields. They call it the quantum foam. I'll explain that to you. And light is actually dark matter and dark energy as it travels in the vacuum, which is not a vacuum. They call it a vacuum of space. It's not a vacuum. It's saturated with particles. First of all, there's dust and debris of every type, and there's light. Light is a particle, so I don't care what they say. It is not a vacuum. And I can show you that, and I will. Light is vortex electrons, spinning electrons, and Rod Warren did this research a few years earlier, and I picked up on it, and then I wrote the paper on it, and this all enforced my research. Now, he was just experimenting and ran into this, and so I, at this point, put out this YouTube in my old station. I don't have this anymore. It was called Mudfossils. This goes back 7 years ago, and I put down all the things. That light is dark energy and dark matter in a vacuum of space. Now, let me show you my evidence to support what I'm saying. And they also agree with this at CERN and Fermilab. Now, don't forget now, this is 7 years ago, and we had all this stuff done. I was explaining all about all this stuff, and then I showed all the evidence to support it. These are the photons. Wait till I show you. And this, I was trying to get through to Fermilab, and that was a disaster. But I'm showing all these particles, and this is back 7 years ago. I showed light spinning and light advancing, and what light waves are, and how light spins instead of flaps like this, and how light accelerates and how it splits and divides. I showed everything, all this stuff. And Rod Warren did all of these just playing around. He didn't realize what he was doing. And this is exactly what he used to do everything I just showed you. All right? except a green laser is different than this, but this was a pulsed, this is exactly the same laser. I did all the same stuff he did, but he's much better than I was. So these pictures are the stuff he shows. But this goes back to 2016. And we were working on this since I think it was 2012. Was when we first started together, working on this together. And it went years and years, and he's growing a little weary of this, it appears. He doesn't really want to be involved anymore. And I don't blame him. It's, you know, nobody pays any attention. What do? You just keep showing it over and over, and that's what I've been doing. But now, they're starting to try to make claims back against me, and it's just not working for them. Okay, so here it is. This is the phone right here, the Galaxy S3. Now, we used the selfie side to take the pictures. It seemed to work better with the selfie side than the regular normal camera side. Now, this came out in 2012, and so we were doing that research up until 2014 or so, 2013, when I saw this. All right, what Rod did was he created a Venturi by using 2 finishing nails. That's all he used. And he shot the laser through that. It was very tight, and he got all the way down to using needles, sewing needles. Very tiny slit for the light to come through, which forced the fields to compress and accelerate. That's what a Venturi does. Now, here's what light does. This, and I will show you that this is not, this is, they've seen this, they understand this. This is light just pulsing through here. If you look, it's this right here, point particle they call it. And it consists of a black and a white particle. This is not me, this is from Wikipedia, point particle. But let me show you even better than that, is from 2013, and I contacted this guy, Don Lincoln. And these are the particles they saw. But they see them spread out because when they explode things, they hit things like this together and they splash all over. We're using light, so we're down in that range. We don't have to splash things. We can see the actual particles. But this is the point particle, which can get big and small, and that one's the fixed particle. So this is understood by CERN and Fermilab and everybody back to 2013. So I tried to interact, did not go well. Okay, I believe I have shown you the Fermilab article showing the point particle versus the fixed particle. Well, the point particle and the fixed particle together make up the Dirac neutrino, and I'll show you that. You see what they're showing here? The glowy part and then the dark part, and they're actually even showing a dark edge over here and not a dark edge down here. This is basically light coming across. They don't understand that light is made of 2 dipoles, not one single like that. And they also don't understand about the proton. Protons, it says, is a combination of 2 up quarks and 1 down quark held together by gluons. Well, this is what a proton is. And every one of these is a dipole. Every one of those little magnetic balls is just a little magnet, has a plus and a minus, exactly like this basically. When you glue 1,823 of them together, they get stable. And that's the first stable particle. The only smaller stable particle is light. And light is a photon, and that just consists of 2 of these back to back. I'm going to show it to you right now. But this is what they think light, or actually electrons are, or protons, I mean. And electrons, they have no clue. It's totally lost. And this is what they show as light, which is similar to light. I'll show you the actual light. And I'm going to tell you the progression of how all this stuff happened, because I tried to interact with all these people, and it did not go well at all. All right, remember carefully these statements. The fixed particle is the black one, has a glowy edge around it depending upon the color. And the point particle gets big and gets small and can squirt like a toothpaste. Now, between the 2 of them together, they make up what they call a gluon, which is actually a Dirac neutrinos. I will show you this. Now, they're going to talk about the quantum foam in a second. But here's his final statements about these two different particles together. Now, he says the extended particle has a fixed size. That's the black one. Never changes, ever, never, ever. It may have a fuzzy edge around it, which it does, depending upon the color. The point-like particles are mathematical abstractions with zero size. Now, I find that hard to believe, but I do agree they have almost no size whatsoever. But they do have some mass, and I can show you that that's true. He says no. It says even zero-size particles have an extended field, which it does, due to the effect of the field surrounding them. Surrounding what? If there's nothing there, it's zero size, what's it surrounding? It's surrounding something because electricity does have a weight. When you charge up your battery, you're putting nothing but electricity into it, nothing but electrons. That's what you do. When you charge your battery, it's strictly the white part. It's strictly this glowy part that goes into your battery. That doesn't go. You just got to strip that off, and that goes in your battery. And your battery almost gains no weight whatsoever. I agree, but it does gain a weight, and I know for that for a fact because I worked with the weights and measures. Now, quantum foam is what's in space. It's everywhere. He's saying that empty space isn't empty. That's an absolute fact. There's no question whatsoever. It's saturated with particles, and all of these particles have fields, and everything that comes through it has to plow through those fields. So light slows down and speeds up. It depends on which field it's going through and how it's being drifted through the universe. But this is the key right here. Listen to this. He says the foam on a head of root beer is complicated. Bubbles appearing and disappearing in a dizzying display. Empty space experiences similar activity, the subatomic particles winking in and out of existence. These subatomic particles are real and have a measurable impact on our universe. Subatomic means they're below the atomic structure of the atom, so they're small. And that's true. These are light. So what happens? Light comes here, and then there's another light particle over here. It goes blang, and I go blip, for it's just instantaneous. And it's like that foam on a root beer. It pops in and out instantaneously. And he's right. He's right about what he's saying. This is 2013, and I contacted him all about this, and it didn't, like I said, it didn't go well. And I said, I can see this stuff with CMOS. He says, no, you can't. Nobody can see it with CMOS. I said, yes, I can. He says, no, it would destroy the CMOS. I said, no, we're using light. We're not using what you guys are using. You will destroy the CMOS. Because what happens with us is we're using light. This was built to see light. It's not built to see this. Smashes the CMOS, destroys it. It is built to see a single particle of light. That's what it's built for. That's what these pixels do. Now, and again, we use the selfie side. Right? And all these things were done with the selfie side and like this out here, and then this was portrayed up in the pattern in the back showing this light spinning. All these different things were done with this. Straight on, to the side, from top to all that. All right, so he's confirming everything that I'm saying. 100% of what I'm saying, he's confirming that space is filled with particles. That's ether particle theory. All right. Now, a friend of mine is putting these books out. They're not my books. They're just made from my papers. I have nothing to do with the books. He's just putting them out, and which is nice. At least it gives you something to see. And, you know, they're not really, and a lot of stuff may not even be right anymore. Because this goes back, this one's from 2019. I keep finding things that, you know, you change. You're wrong about a lot of things. You have to be wrong before you can be right. Nobody is right instantaneously. It just doesn't happen. It's like spontaneous rightness. It does not happen. All right, this is the most important thing to understand. It is saying that it is only by their light, which they don't understand what light is, that we can begin to understand the exotic physics that govern the galaxy near the cosmic dawn. They're trying to look back in time, and they don't realize light slows down. They say these things are ancient because they're so far back. No, they're just slowing down more and more and more. And I can show you this. It's very, very obvious. All right, don't forget, everything we know is based on this light, and light never changes speed. It's coming exactly the same speed as when it started, which is just nonsense. And these are the images. Look at the debris that's in space. Think of the fields that all these particles have to pass through. And they claim it's just like there's nothing there. It's just saturated with particles. Absolutely saturated. How can they possibly think that that particle coming through all that debris has no effect on it? I'm going to show you what fields look like. There's Jupiter in a red spot, and they don't understand that either. So I'm going to show you all this stuff. I think I understand what's going on out here, and they don't. And it relates to all these particles being... All right, you see this? This is from Argonne National Labs, and they can see light in this particular way, the same way we see it here, in a non-defined way. When light is just going through the atmosphere, it just sort of glows, and everything in front of it has to glow, exactly what I'm showing you there. You see this right here? Out here, you see the little waves and all that stuff. They're showing it. Basically, this is correct, except inside of here, it's not just one particle with a black and a white. It's two blacks and two whites, which is a photon. And here's our photon right here. Well, first of all, let me just show you what our light wave looks like. You can't see the photon yet, but it's the same thing. And these are pulsed lasers, pulsed red laser. And all of these are glowing, just like it showed you in the other one right here. But not only can we see the wave, once we accelerated it, and here's the acceleration phase, you can see it's quite obvious accelerating. Then the little tiny particle starts to gain energy. And you see it's starting to glow. From here is where the particle was originally, creating this big magnetic field as it came flying through the air. Now, because of the Venturi down here, the acceleration phase has kicked in, and it's starting to accelerate. They call that neutrinos, and they change flavors. They get stronger and stronger and stronger until they turn into a photon. I'll show you that. And then here at the Venturi, because of the pinch at the Venturi, only the white can get through. The black, which is fixed, it was too big to get through. So you can see what's happening here. There's acceleration, and virtually no question about it. And it's pulling itself right out of its wave. So this is light accelerating. If anybody can contest that, I would like to hear their argument against that. Okay, don't forget, everything we know is based on light. And this is what they show for light, which I can agree with that. That's a light particle, only this is from Argonne National Laboratories. Now, they can see there is a glowy center, yes, and then there is a field surrounding it, yes, and that field creates all this concussion out in front, yes. It's going that direction. However, it doesn't consist of one tiny particle like that. It's a double dipole. Okay, let's just start right off with the very, very basics. They consider a proton to be a big ball like this with a couple of quarks and so forth, and very, very basic. And then it explodes into a zoo of particles like this when they hit them together, neutrons and protons, and they splash all kinds of particles. Yes, I agree with that. But what they're actually hitting is not these big balls. They're hitting globs of particles, which, in other words, a proton, instead of this, and being consisted of a few quarks, it's consisted of 1,823 actual dipole electrons. And two dipole electrons, and each one of these magnets is a dipole. It's got a positive and negative. When they glue together, that's the smallest stable particle there is light. And that has a field around it. And when it hits something, it bounces back, depending upon how fast it started out and what it hits. The hardness of what it hits, basically. Because that's what energy is, something banging into something else. And this is energy right here. Whoops. And it's all about high luminosity now. That's luminosity. And all of these things are being concussed as the light comes through the air. Let me turn that off. Sometimes it looks better this way. Now, you can see all of these are fields that are also glowing, as this field is as well. All right, so That's just the beginning phase of acceleration. Then we get into this phase, as I showed you before, and the particle is actually disassociating from the wave. It's just pulling itself right out, and here it explodes. Here the black separates from the white. And when I say the black and the white, here's what they are. All right? There's a black and a white particle here. All right, this is just the black and white showing. This is what it actually looks like colorized. And this is true colors. This is from a red laser, and they talked about that in the Fermilab article, the point particle and the fixed particle. Fixed particle has a glowy edge around it. And here it is right from there, that article I believe I showed you. That's the black. It never changes size. It's all that does is attract the white. The white wants to be so desperately attracted to that black. That is what you'd have to call the strong nuclear force. All right, they're tight. They are tight. And to break them apart, you have to do a lot of work. However, we just got lucky. We just got lucky. Because with the Ventura, you don't have to do any work at all. You don't do any work at all. It happens automatically. These particles come down, and normally you have to pull the white apart from the black and send the white into a battery and let the black go somewhere else. Well, guess what happened? This is what happened. When it went into the Venturi, the black separated from the white. Remember here, the black and the white were together, and they're supposed to be held tight forever. They're never supposed to come apart. And here they came apart, and then they came back together. You'd have to consider that fission. Something breaks apart, it's fission. When it comes back together, it's fusion. Now, this right here, from the wave accelerating and the particle, the neutrino phases, then the photon phase, then the explosion phase, and then the recombining phase here. What happened right here? Here it is right here. That's it right there. You see the black is separated from the white. Now they know this at CERN and Fermilab and Argonne and all of them, Lawrence Livermore, and I've contacted all of them. And I never got anywhere anyway. The muon neutrino is the black ball. That's that black ball right there. That's the muon neutrino. All right, and it's the same thing. Don Lincoln would agree with that, I'm sure. And this is turned into a sterile, all by itself, muon. That's the cat's meow. The white has turned into an electron shower. You see the electron neutrino? And they were supposed to be together, excuse me, right here, the black and the whites. Just one of these together is what you would call, oh, excuse me. Okay, sorry about that. Now, that's the black and the white, the fixed and the point particle. Point particle get big and small, and here it is happening right in front of your very eyes. You see that one's tiny and this one's big? Well, why is that one big? It's because it's concussing with all these little particles that are in front of it as it goes this way. This is shielding this one, so that gets smaller. And as that charges up bigger and bigger, it'll flip. Then this one comes in the front and it charges up, and then it'll flip. And that's what the muon wobble is all about. And they spin. And I can show them spinning. They're very, very simple to show you that. And this is the whole process in one shot. But this is right here. This is, electron showers are supposed to be just unbelievable amount of energy. And I believe that's true. Because luminosity is energy. All right, but back here you had almost no energy at all, no glow. Look at that. It's glowing so much, it's exploding backwards like an atomic bomb, radiating backwards. These are radiating backwards. These aren't hitting forwards. This is being pushed back at. This one's being sucked forward, but these are being pushed back at because of the explosion. Just like it's really a subatomic nuclear explosion. That's exactly what it is. All right, I just want to set you up for the Diracs. This is all about the quantum mechanics and how protons are combined of two up quarks, one down quark held together by gluons. Well, as I showed you, this ball of little particles really is what a proton is made out of, 1823 of them. Now, it comes back up to here, point particles. They're going to be talking about the Dirac. All right, so what is the Dirac? All right, here's the Dirac right there. And they show it sideways. They will always be up and down this way, black and white. All right, that's up spin and down spin. because of the polarity of the Earth. So they're showing them sideways, but I don't. It is the same. It's a black and a white one, but it's not. In other words, if I took this black and it's hard to explain it, but this is the majority of neutrinos. These are neutrinos. These are the smallest particles that exist, and these ones here are in between becoming an actual photon, Dirac photon, basically. I'm going to call the Diracs gluons, that's what they are. They're the gluons. And back here, they're sort of not energetic enough to be fully shown like this, like I'm showing you. Well, let me show you now. Don't forget black and white. All right, remember this now. Don't forget there's a black and white particle. And these are those particles right here. And this is the acceleration phase. When they come in, you see the black and the white here? They're together, but they're not in a fully formed photon phase. You see, that's a photon-ish. These are neutrinos. And they change values as they stack up against themselves just before they hit and bounce back as a photon. But these have formed fully into the photon phase. However, at the Venturi, it won't let them through. It only lets the white go through. The black bounces back and creates this huge reverse wave. So these are the particles. These are literally photons. And these are neutrinos. See them? And these are neutrinos. They're stacking up sideways and upside down. And they are what they are. And the red and the green and the blue, they're all the same. Here's the green. All right, so here's the green. You see it? And don't forget now, the Dirac doesn't go this way. It goes that way. All right, and it's always polarity towards the Earth. That's why they call it the upspin and downspin. Now, this is the neutrino phase of the green. And this one here, this green, is just getting ready to flip. You see how it's getting overcharged on this one? It's going to go rip, and then the white one, the dim one, will come in the front. And the blue, you really can't see the particle. It's just too fast. But I can show you something of interest. And here's what it is that blue is coming through this way. And it is hot, man. When it comes through, it's sizzling. This is coming through the Venturi. So it's sped up a little bit. Now, you see, all you can see is white dots. And they're almost straight, and then they start to curve to the left here, and then they curve much faster. And then all of a sudden you can see two dots. All right, and then in between, it's just opening up the frequency. So it's shifting to the red, basically. This is hot blue, and this is not hot blue. This is almost getting down to the greenish area, let's say. Let's just say that. It's not really. It's still very, very hot blue. But it's shifting towards the green. Let's go with that. Now, let me explain to you what my nucleus is. All right, this is the nucleus, which is the center core of an atom. All right, they always thought it was just one big positive, and then a bunch of little negatives floated around out the outside. Well, I disagree with that. But there is two possibilities that I do feel are very possible. One of them is that all of the black particles will gather together in the center, and all of the white will crust around it. So you never see the black. You've never ever seen it, because nobody's ever seen photons before. I'm really just about the only one who's ever shown photons, from Rod's work. Now, so you never see anything other than the glowy outside. That's the inside of everything you look at. Everything there is, 100% of everything, has the dark inside and the white on the outside. And you're still going to have it the same way if there was a different structure. And here's the different structure, is where you had a dark core and just enough to hold on to a real tight hold of these blue ones. And they're just tight held like crazy. Now, and then you go into the opposite polarity around those, and then the green attaches basically to that. So you get these layers. I'm tending towards this. I'm tending towards the dark center and the glowy particles on the outside. And then you get just enough to cover what this suction is. all right? And then some more will want to get in. And they'll come up to this region here, and these guys will say, no, we got enough. We just right now. You have to stay away. And it says, well, I really want to get in there. And I say, well, too bad. And it'll say, if you want, you can stay right out there. And they'll say, all right, I'll stay out here. And then another one comes, it might stay over here and over here and over here. And then they come, they pretty much make a ring of 8 surrounding the core, which is the valence electrons, which would be just 1, 2, 3, 4, 5, 6, 7, 8. And then they just keep swelling up from there. And so I can see it's got a very close similarity to the Standard Model. But nobody's ever known that the dark energy was stuck in the middle of all this. By the way, people send me things, and I was working with a guy, and I lost his contact, I lost everything. I lost a whole batch of stuff. I got bumped off of things here and there. So anyway, whoever did this, I appreciate it, and maybe put a note in one of the comments if you were to see this, that I was the guy, you know, because I didn't do this. I just told him, I said, here's what I think. It's either this or that. And he did a bunch of other stuff for him. Real nice guy. And like I say, I lost contact with a lot of people because I've been shut out of places, and once you're gone, you're gone. All right, so I agree with light traveling this way on a bright core, and it makes a wave because of the magnetic field surrounding it. And here's ours exactly the same. And here's ours accelerating. No question whatsoever, that's acceleration. And that is energy, a lot of energy. And here it is slowing down. The blue's coming in hot and slowing down. Green is the same as the red. And here's the particles and the photons. I think I made a very good case for showing you that this is exactly what it is. And in the Standard Model, here's what the Standard Model shows. Where is it? All right, here's what the Standard Model shows. They have all this stuff. Well, everything around here is inconsequential. That's just debris of the center. Now, what is the center made of? Here it is right here. All right, I showed you those photons, gluons, Z bosons, and W bosons. All right, the Higgs is when these come back together and make this big circular field. So this is the only thing there is. All of these are twisted up and down and sideways, and all these neutrinos and all these different values stacking up, and here's what they see when they collide theirs. Watch this. Don't forget, I'm saying this is all that exists is the black and the white. That's it. Those two together make a gluon. That's an electron. Really, it always was an electron, but they didn't know there was any black. Two of these back to back make a photon. That's what I've been showing you. So let's take another look. Don't forget, because they're using such gigantic particles, they're smashing just trash everywhere. So for us, all right, we're hitting these little particles together, and the CMOS is made to accept these particles. It's not made to accept chunks like this. That is a chunk like this. When they hit these together, they have no way of controlling how many particles go to which direction, or how they just go everywhere. So they see all these different bits, but we started with these. We started with these bits, so we never see anything like that. And we don't damage the CMOS. I'm going to give you a little explanation of how I understood that CMOS was the key to being able to see these things, and that you could accelerate using a Venturi, and how I progressed through this whole thing through a lot of pushback, and still the same pushback today. But I'm going to just lay it out to you, because I went to school for this, to the University of Geneva, knowing that they were tied in with CERN. And then CERN went ahead and did all the things that I said to do. Okay, this is trending in education, talking about the lessons learned from this James Webb, SpaceX, and CERN. And they're going to be showing all the different pictures, image from the Webb scope. Look at this. These are the first images. Now, don't forget, they're talking about light coming through this towards us and never slowing down, even though it's being interacted by all these fields. Look at the particles that exist here. Look at this. How could they possibly think that they can see through that and that light never changes speed? It always stays consistent. It's just, it boggles my mind to believe that they could think that. All of these fields push against other fields, and I'll show you these fields. All right, let's just start out to be sure you understand. I showed you light can speed up through the Venturi. There's no question about that. And this is light slowing down. I would say there's no question about that. This is done with CMOS, and all we're looking at is the light particles. That's why we're not damaging the CMOS. Now, I presented all this information and discussed, because that's my background, is chemistry and physics and all that stuff, and quantum. And I said, you know, we can use the CMOS because we are only using light. It is designed for that. But you guys are smashing it, because that was the big thing. Oh, you can't do it, it's impossible. So I finally convinced Geneva. I went to the University of Geneva because they're tied in with CERN. And I figured maybe I could wheel my way in there. And I did. And they talked to me, and I showed them all the stuff. And at first, it was a very serious pushback. Oh, you're crazy, you know. Basically, they didn't say that. They were very, very nice. Absolutely, quite respectful. I was very shocked, to be perfectly honest. And at any rate, they did listen to me. And when I finally convinced them, and I believe I did convince them, that we could use a CMOS, and in addition to that, we were focusing using the Venturi. And that's how we were getting such spectacular results. And I mean, the results are spectacular. Right? There's no other way to put it. There it is right there. That's fission. That's fusion. This is the dark matter, dark energy. It's just black particles that nobody's ever known about before, basically. And they say, well, you can't find dark matter. It's every day they're talking about dark matter. I've been showing this for minimum 7-8 years now. This is the electron shower. It's supposed to be unbelievable quantities of energy there that we should be able to harvest. And I've been showing this little thing that I think could do the job right here. It's simple as this. Can you see that? Right where this here is coming through, all of this is a restriction. We don't do anything whatsoever. The white comes all by itself, comes away from the black. Usually you have to do a hell of a lot of work to force those white particles away from the black. We just put it through the Venturi. That is literally free. And if you could put a harvester right there, something, design it correctly, you could get literally all of that. And it just is, at this point, it has no weight and no mass, just like it says from Fermilab. I agree with that. It's just burn. And that's what you want to put in your batteries. When you charge your batteries up, you're pushing just nothing but white in there. And that's why you can charge up a Tesla or whatever, and they say it regains no weight to speak of. And, you know, it does gain weight. I absolutely no question whatsoever. Something that's hot has extra white particles in it. That's hot. And it does weigh more than something that's cold. But so small, they say, you can't really measure it. They can measure it, the weights and measures, and I did work with them. I didn't work with them, but I had to have my weights certified there. And when they did, they said I had to leave them because they had to be the same temperature as the other ones. The only thing with temperature is excess electrons. They will bleed right out to where they want to be accepted in a colder area, or the hotter area will push them into the cold thing, and they'll all become the same temperature. Once they're the same temperature, they weigh the same. That's the point. But all we need to do is harvest that white energy, push it into the battery, and you drive around all day for free. And you really don't even have to have a battery, because that can run all day long. And all you're using is the tiniest particles that exist, the muons and electron neutrinos. So there's no real damage that I can see is going to happen here, but who knows. You'd need to have something here that would accept all these different frequencies of light, and they have them now. They have perovskites, somehow, I'm not sure how to pronounce it, but they're just thin film metal. We have all different oxidation states and different molecular orbitals in there, which bang into different frequencies and collect them as electrons. And these are just electrons on steroids. That's all they are, is electron neutrinos, all by themselves. Very hard to do that. You see this? This is what they're looking for, these gravity waves now. Like, they can't find them. Well, Rod's nephew, Dylan, got a new phone, went out and took these pictures. This was a few years ago. He sent me these and it blew my mind. And that's the last I heard from him. He sent me the pictures and I haven't had any contact since. But what he did, I don't know what app he used, what phone it was maybe 3 years ago or so. And these are gravity waves, but actually these are electromagnetic interference waves of spinning dipoles. Everything is a dipole. Whenever you have a dipole and it spins, it creates these pulses. And that's what it is. And the further they get away from the source, the wider they become until they just fade out into nothing. But every single one of them has a field. Every single one of them. And some of them are very strange looking. Some of them are beyond belief, actually. Like up here, I don't know what to think about this. This kind of scares me a little bit. But they talk about redshift. Well, there's blue shift also. Blue shift means that you're crushing the light and making it absorb energy, making it more energetic. That's what this is right there. That's blue shift. This side has more to the red shift because the moon is going this direction. And it's concussing with the light that's in front of it, making that light, which normally you wouldn't see, making it just glow a little bit into the blue range. It's not spinning, so you don't get this. And the moon apparently is not a dipole. And it appears you have to have a dipole to spin. I'm not sure. The dipole does spin. There's no question about that. And they all spin. And then these things here, I don't know. That's about as strange as it gets. Look at that thing, man. Yikes. And this is either on top of the moon or in between us and the moon. Those are energetic looking regions. Anytime you see in black and white, you're seeing energy and no energy. Energy and no energy. That looks like Atlantis, and this looks like the pyramids of Giza. I'm telling you, it's starting to scare me. You know, the one thing I didn't show you is the Higgs. But don't forget, the black and the white are the only two things that exist. They make gluons, they make photons, and then the next stable particle is a proton, which is about 1823 of these gluons together. Now, so let's start with that, and I forgot to show you the Higgs. Here's what Higgs look like according to CERN and Fermilab. All right, these are all these little fields, and they're showing particles escaping. They don't come back, but the red seems to stay around because it's the weakest. All of the real tight ones that were right down at the core, for them to get away, they really have to take off. And they do, and they're gone. And that creates light. All right? The reddish stuff stays around and doesn't leave home, basically. Now, here's what we did. This is our Higgs. All right, there's where that white comes down, and it just creates these spinning disks. These white particles seem to fuse in with the black and just make these spinning disks. And they see this at CERN and the Fermilab. It's not something that's unknown. They just didn't know. See, but they're seeing a whole batch. They're seeing these things just everywhere, flying in all bits and pieces. But they all make these circular patterns, and then they have all this stuff to look through, which means nothing because it's just bits and pieces. And they call it a particle zoo. This is their particle zoo. It's everywhere. And we started again with the smallest particles that exist. So we never got any bigger than this here. This is as big as we got. Even with the green, the blue, the red, doesn't matter. They're all this size when you're down in the light range. And the only thing is the spin and the speed is different. Now, I can't tell you whether the actual speed of the particle is faster, but I can tell you one thing. It's much more energetic. See that green? They're both of them, the red and the green, coming through at the same time. Red, we know, is the weakest particle. The green is much more powerful. Then the blue is like off the charts. You can see the green just push the red right out of the way, get out of the way, and then reconcussed way out here. Now, would it have shown here? I don't know. It had to get through this field that this red was puffing up here. So it may not even have shown until it hit way out here. I'm not sure of that. But the red immediately starts to decay. And this, as I told you before, these will never spin any way other than this way. You're never going to see them flopping around like this, except for here. And the reason is the red was so much more powerful than the green, it forced the red to just barrel roll. See it? That just doesn't happen. They don't do that. They do not do that. These particles come through spinning like this. All right, sometimes they're very long like this, red, slow, or sometimes they're fast like this. And sometimes they're blue, they're like almost just... Now, it determines how energetic that leading tip is going to be, because that's where it is. So all I can say is it's the same particle, the green and the red and so forth, they're all the same particle. And the blue, it's just the speed of the spin. And they do spin. They don't flap like a wave. All right, this is light spinning. It spins this way and it spins that way. It's all over here. There's a whole batch of them, zillions of them coming at the same time. And it's being forced through that venturi. And so they're really getting crushed in the center, glowing. And then less glow, less glow, less glow. But they're still pushing away from each other. These do not want to touch. It's called the Kashmir effect. They can get close, but they can't touch. It goes this way, and some come over this way. So that's why you're seeing them on both sides. And they set up these patterns which are exclusion zones. You stay there, I'll stay here, you stay here, and then they zip, 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 and that's what's called interference. They always thought it was like two slits, and it would go like this and flap over this way and that way. This is a single slit. It has nothing to do with a flappy wave. It spins, and that just proves it right there. And I'll show you from the sideways. You can see it spin too. Here's from the sideways. Same thing with the blue. You see where they get close together in a little bundle? They hate each other. They just literally hate each other. They, stay away from me, I'll stay away from you. If you come near me, I'm going to glow and I'm going to push you away. I call it push to shove. All right, and they're pushing and shoving. And when they get like down in this range here, it's all over. It's case closed. And the blacks can't get through with the white ones. And at this point right here, that's supposed to be minimum 200 times more energy than you started with. If you can separate the black from the white, you should be able to recoup 200 times more, minimum. And it could be much, much, much more than that. And you see the luminosity here? You see that? Almost no luminosity. Luminosity is glow. This is on steroids. And this is exactly what CERN and all of them want to do. And you know what? I'm going to tell you some stories about my interactions from 2012 when Rod started using this Galaxy phone, and I picked up on it, and I said, oh, let's work together, and he did. And he deserves credit for what he did. I'm telling you, I could have never done this without him. All right, so I'm looking all over to try to get somebody to look at my stuff. So I figured, well, I'll go to Yale and take their courses there. It's free. Quantum mechanics, key experiments, wave-particle duality. They're going to be talking about the double slit experiment. Now listen to how he starts it off. This is Professor Shankar. Now listen to this. This is the first day of class. All right, so like I say, these are free. You can come up here and learn if it's something you want to learn. So I tried to engage, but listen to the first words out of his mouth. Listen.
So this is a very exciting day for me, because today we're going to start quantum mechanics, and that's all we'll do till the end of the term. Now, I got bad news and good news. The bad news is that it's a subject that's kind of hard to follow intuitively, and the good news is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys, because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. right now, I am the only one who doesn't understand quantum mechanics. In about 7 days, all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else. That's the only legacy a teacher can want. So, all right, so that's the spirit in which we are doing this. I want you to think about this as a real adventure. Try to think beyond.
All right, he's right. Nobody can understand it because it's just not right. There's no way to understand it. Light does not go the same speed. It slows down, it speeds up. There's all the kind. They won't pay attention to what I'm showing them. So I try to explain it, and of course that didn't work out. All right, so I can't get anybody to listen to me. So I figure, well, I'll take a course at the University of Geneva because I know they're hooked in with CERN. So I did take that course, and I showed them all my stuff, and they listened. You know, I had professors, and they listened, and they were very nice to me, actually, to be perfectly honest with you. But I didn't get anywhere with them. I said, can we do something? Can we collaborate? Can I do anything with you? And they said, no, you will. They said they would follow me on Facebook. I'm not kidding you. I got thrown off of Facebook, so I lost everything. I lost everybody. That's the way it goes. But I did show them this, and then shortly thereafter, they made some changes. All right, so after I went there, this is from CERN themselves. This is 2019. Detectors and experimental techniques. They're going to upgrade CMOS detector and system development for the LHC detector upgrades. That's the upgrade they did to use CMOS. Now, they still can't use the same kind of CMOS I'm using. They had to harden it. They had to make somebody put some kind of filters on or something. I don't know how they hardened it. But otherwise, they would destroy it, yes, because they're hitting it with chunks like this. This is absolutely damaging when it's going the speed of light. A chunk this size is just like an atomic bomb. So that's the first thing they did. Then they also did the focus. All right, so here's the other thing. New technologies for the high luminosity. Well, luminosity is the energy, high energy LHC. And the high energy, luminosity is energy. The beam focusing, so they upgraded to focus, injector upgrades. So here it is right here. Luminosity is the object's measure of its intrinsic brightness, or the brightness, the luminosity. It's defined as the amount of energy the object emits in a fixed time. We're emitting it through our Venturi. It is essentially the power output of the object. This is the power. And as such, it can be measured in units such as watts. Luminosity creates watts. Watts are energy. Watts make your car run, make your lights work, make heaters do that. Watts are particles wanting to get back to the other particle. It's electron flow, basically. And the more electron flow, the more wattage. All right, it's amperage, wattage. There's all kind of, it gets a little tricky, but trust me. What they are looking for is essentially the power output of the object is the glow, the brightness, the intrinsic brightness. So this is the problem. Look at this. We can do this right now, is to focus and using light. They're going to look for high luminosity at the Large Hadron Collider. The high luminosity LHC project aims to crank up the performance of the LHC in order to increase the potential for discoveries after 2029. All right, they want to increase it with the number of integrated luminosity by a factor of 10. So they want to get more and more collisions, and the only way they can do that is to focus, and then, you know, they could be able to see them with the CMOS, but they have to focus in on these beams and make them hit head on. If they're going to use the head on, we used the same thing, but we made them go sideways. They collided, the field's crushed. Same thing, but it was sideways instead of head on. And head on is very hard to accomplish. All right, you see this is all this is. It's a Venturi, and it's a rounded Venturi like this. And literally this is what Rod used. Is this laser, this exact same laser, Bosch GLM 15, and this exact same cell phone, Samsung Galaxy S3. And this is back 2012. So this comes through here, the light comes through that, and this creates the slit. And because it's rounded, as the light comes through, the ball of light has to squish down like this. And when it does, the black can't get through, but the white can squirt right through, and it does. And that's exactly what happens here. And because we're only using light, it doesn't appear to damage anything here. And we use the selfie side to take the pictures. And Rod just did a fabulous job. That's all I can say. Without him, this would just be totally impossible. You know, this is kind of crazy. We know from just this picture that the black can push the white. The black and the white are going this way together. The black is behind the white pushing the white. It's pretty obvious. So the black pushes the white. That we can see because it's coming through the venturi, and some black is coming through with some white in this particular venturi. So we know black pushes white. Can white push black? That's the question. Now it appears to me that the Higgs fields are the end result of the white being completely separated and then smashing into whatever it is here, and then they turn into these Higgs fields, which a Higgs field to me is going to be the reattachment of the black and the white, and then they make these spinning fields. And they know about the Higgs fields. It's not something I'm making up. They know fully well about them, and they see them, but this is what they see. You see ours here? This is what they see, because they're starting with huge particles. They have all kinds of different little bits and pieces, and that's why they get all that particle zoo. So I think we got a better way of doing this, and I can see these fields pretty well. And I'm trying to figure them out as best I can, following. You see this one here? This is the best one I can see. You see this coming off like here and bang, right into here. It almost looks like it's hitting a little black particle. You see the little tiny black and white? And then it looks like it's turning into a spinning disc. I don't know. But I can see this black one's trying to grab into the white ones here and there. This one just happened to be pretty good. And this one here is not too bad either. It looks like it's hitting that disc. It's very hard to make heads or tails of some of this, but I do know this is the white particles. They're separated from the black, and now they're coming back into these Higgs fields. It happens every time. Every single time. You see, this is coming through the venturi this way, and now we're looking into the venturi this way. And here's the particles coming out at us, forming these fields. So they always turn into this from the white. So I would guess the white is either pushing the black, it appears to be pushing back into the black. That's what it looks like to me. And then this one here, yikes. I do understand that one now after, got to be 8 years of looking at it. Okay, I go way, way, way back with this stuff. This was from 1970. This was a paper I wrote about dipole molecular moments of polar molecules, and I was doing PCl3 and trying to figure out where the centers of positive and negativity are. Dipole moments, where do they exist within that molecule? All right, because it's a pretty tricky little molecule. Anyway, I came up with the fact that there is no such thing as just negative particles and positive particles. Although there is. Here's where it gets tricky. There is those such things, but they are on a micro scale. They are the elementary particles. This is going to be a little hard for you to understand, but, well, maybe it won't be. I think I can make it understandable. But anyway, my point is, I understand this stuff. I will show you. And I wrote this paper 2016. I was going to call it nuclectron theory, which means nuclear electrons. They always said outside the nucleus was the electrons. No, the nucleus is made up of electrons, and electrons are made up of muons and the white and the black particles, which are muons and the electron neutrinos. Those two together, and they call them diracs. And I was writing all about this and saying everything's wrong. That light has no mass, wrong. Light's fixed speed, wrong. Neutrons neutral, wrong. After that, the pure guesswork. And then I went on, and this the whole thing ends right here. That's it. That's my whole paper about it. And of course, I have the mud fossils and all that stuff. And I was really upset at this point. I said, Mudfossil University does research and theory. Others can judge. Mudfossil University is free for all resources and are not available to expand this knowledge base at MFU. Are not available. I urge anyone that has the facilities to do experiments and debunk or confirm, but do not ignore these things. This is real. And then I have this video right here, because this was always done by Rod Warren in Australia, these experiments. And I show that light is dark energy and dark matter in the vacuum of space. This goes back 7 years ago. I put this up, and this shows what I'm claiming about light, and I even actually figured out how much the Earth is growing. If every particle weighs, which it does, I believe 0.000585, somewhere around there. It's the weight of each electron, and the Earth is absorbing so many electrons per hour. And Earth's mass is increasing substantially. There's enough light hitting the Earth, and it has a weight, no question whatsoever. When it comes in and it hits the Earth, it has a weight. The weight is the dark part. That's the dark energy and the dark matter. That's where the weight exists. And they know this. They say we can't find 85% or 95% of the universe because it's dark. Well, it's attached to the white parts. That's why you can't see it. Because the only thing that bounces back at you is the white parts.